My name is Jim Kudirka. I'm a solutions architect. I consult as an independent solutions architect. I coach, I train, and I consult on architecture and software engineering best practices. I've been doing this now for a number of years, and one of the advantages of being an independent consultant is I get to work with a lot of different teams within a lot of different organizations, sometimes at the same time. For example, I have 4 systems I'm designing simultaneously right now as an architect, and I'm helping different teams learn some of the things I'm going to share with you today. And so what that has done for me in being an independent consultant is I've gained a unique perspective across the industry, and there's a lot of common practices that everyone's doing. And so I'm trying to encourage this idea of applying engineering principles to software development. And so I have in here this opinion of mine is that we have a pervasive lack of critical thinking. And so let me give you an example of that. I've used this phrase before on different presentations. Would you ever hire a team of skilled laborers to build your multi-million-dollar dream home without blueprints? Rhetorical question, of course, but no, of course you wouldn't. But the vast majority of our industry is building multi-million-dollar software systems without a design. And I see it every day on many different teams and many different organizations, and I'm trying to combat that. That's that lack of critical thinking. If it was your money being spent on that multi-million-dollar software system, would you do it that way? Here's another question. This occurred to me recently. You can build a home and have 11 to 12, typically 11 or 12 months of warranty. You can buy a car and have several years, tens of thousands of miles of warranty. You can buy a toaster and have a year warranty. What if industry-wide you are required to warranty your software, free of defects, for at least 90 days, meaning either you give us back the money we paid you, if we find one, or you fix it for free? Would you continue to develop software the way you do today? And so that's that pervasive lack of critical thinking I'm referring to. So I've been a professional software developer and architect for over 25 years. I've been leading software development teams for over 20. I've always been in the code, always practicing my craft, and the strangest thing is I was always the architect on virtually every system I've built. There's 2 occasions in my career where there was another person who had the title of architect on the project, but I was helping architect in both cases. I never considered myself an architect until I got trained by an architect, by a master architect. So that was the interesting thing. I never had the title either. But I've always been in this continuous pursuit of improvement, and I've invested heavily in my education. I continue to do so today. So I'm constantly learning from others. I work with great people, and the funny thing is when you work with great people, some of that greatness rubs off on you. You ever heard that before? And that's what's really enabled me to be up here and be able to share what I've learned. I specialize in applying the iDesign method. How many of you have heard of iDesign? Raise your hands. Oh, quite a few. I'm usually getting like 1 or 2 hands when I do this at like a developer conference. All right. So I specialize in applying the iDesign method. I've went to almost every training that iDesign offers, some of them twice. Over 300 hours in training with master architects Joao Lowy and Monty Montgomery from iDesign. Next month will be a full 10 years that this is all I've done, is applying these concepts I learned from iDesign. It'll be October of next month. So the strange thing for me was I was always able to put these concepts from my training into practice immediately on every project after every training. So I was always in a position to be able to apply those concepts. And I think that really resonated well with me and helped me to understand it better, because it didn't just languish and I forget about what my training offered me. I've met a lot of other people trained by iDesign that still to this day are not able to put into practice what they learned. So that was unusual circumstances for me. Very fortunate. I'll make a few references, many references to Joao Lowy's book, Writing Software. I got a copy here. This book was written after I learned all this that I'm going to share with you today, and years after I began practicing it. So the title of this presentation today is the 6 tenets of modern software engineering. And we're going to talk about the 6 tenets. But first, I want to share with you a bit of what I mean by modern software engineering. So the evolution of our industry. Now, I'm taking this from the appendix of Programming WCF Services, another book by Yuval Lowy. And I found it interesting that he had this captured all the way back in 2007. I have a first edition at home of this book. So in 1960, we were developing software in COBOL and Fortran. And then 1970s, C and Pascal emerged. But at that point in time, the unit of reuse was still at the function or procedure level. Then in 1980s, Smalltalk and C++ emerged, and then now we had the advent of object orientation. But even then, the level of reuse was always at the class level. In 1994, COM came out. The unit of reuse now was at the interface level. 98, Java 2 EE came out, and then 2002, .NET 1.0 was released. Get that right, Matt? I had the date wrong once. But at that point in time, .NET was built on top of COM. A lot of people didn't know that. It's no longer the case, but back then it was. You could look at an integer, and it had a GUID behind it. It's also implemented, I think, 15 different interfaces just on the int type back then. But at this point, we're still suffering from that lack of interoperability we're really after. .NET code could not call directly into Java code back at this time. But then in the late 2000s, service orientation emerged. And now with service orientation, the level of reuse was now at the service level, exposed through endpoints, and there's a myriad of choices we have for communication between services, right? Starting off with like just basic RPC, SOAP, WCF. Now we have REST and web APIs, gRPC. So finally, Java code can call .NET services, we can call Rust services. Basically what this gave us is the ability for us to cross the language boundary, the framework boundary, the platform boundary. And so finally, service orientation achieves that ever-increasing desire for that loose coupling and standardized plumbing. And our goal should always be that we have off-the-shelf standardized plumbing for all the projects we build, because we really should not be experts at plumbing. We should be experts at building business value to our organizations through the software we produce. Plumbing is just something we leverage to get us there. So I had some feedback once. Thank you, Chris. These are the 6 tenets of modern software engineering. So loosely coupled, highly cohesive, logically consistent, extensible, testable, and maintainable. Now I know what you're thinking, that this is the way to software excellence. This is the way. And you're right. This is the way to software excellence. And we're talking about that. What does it look like? So we all know we should have systems that employ all 6 of these tenets. We're all building service-oriented software systems today. But what does it look like? Does every team member understand what loose coupling, how we achieve loose coupling? Every team member understand how we create highly cohesive and logically consistent interactions in our architecture and in our code. So let's look at what is required for us to achieve that. But first, I have this statement that I've been using for quite a while. It ties back to this. So our job as software engineers is to design and build loosely coupled, highly cohesive, logically consistent, service-oriented software systems that are extensible, testable, and maintainable. This is our job, whether we accept it or not. This is what is expected of us. And so understanding what it takes to do that and the techniques used is important to us. So it looks like this. This is a roadmap of design that I share on all of my presentations. On the left, we have system design. And this is, again, the iDesign method being employed here. So left, we have system design, where we gather and analyze requirements, we perform decomposition, and we document our architecture. In the middle, you have project design or development plan design, where we get estimates, we identify the critical path, we identify and quantify the cost, schedule, and risk. We use earned value tracking to track the execution of our project, and then that helps influence our backlog. Not every team member on the team does project design. It usually only needs one person. But somebody needs to influence the order of the backlog to most efficiently assemble the components into a software system. So if you think of system design as the blueprints for my software system, then project design is the assembly instructions for those blueprints. And then on the right, we have software engineering best practices. We have detailed design. And detailed design is where we design the code inside the components in our architecture. It's where we look at the interfaces, the factoring of service contracts, and the factoring of data contracts that are passed along those operations in our interfaces. They're how we're exchanging data from service to service. And then finally, we have the zero tolerance for defects mindset for achieving that impeccable quality we're all after. So we can warranty our software, right? So I'm primarily going to focus on just system design and detailed design to achieve all 6 of those tenets of modern software engineering. So we're going to first focus on loosely coupled. So what is loosely coupled? It's changes in one component do not affect the others. With system design, it starts off with a layered, closed architecture. So I'm now quoting page 60 through 82 in writing software. Duvall teaches that layers layer in encapsulation. All right? And there's very specific rules of interaction between these layers that helps us with that encapsulation. You can only call one layer down from the client layer to the logic layer. The business logic layer can only call one layer down to the resource access layer. And the resource access layer can only call one layer down. You have this vertical bar of utilities on the right. The utilities are just framework components that do not have any use case specific business logic in them. So they're shared across all the layers because of that. So a closed architecture, a layered closed architecture, facilitates loose coupling by itself. And then we introduce a decomposition using volatility. So encapsulating potential areas of change into components further facilitates that loose coupling. The interesting thing about these concepts is that they're not that new. They're over 50 years old. Dr. David Parnas wrote about this in I think it was 1971. And so since we're encapsulating potential areas of change into the components in our architecture, Dr. David Parnas says those difficult design decisions should be designed so that they encapsulate them from each other. That's that loose coupling. That employs that single responsibility principle from solid, right? A software entity should do one thing and therefore only have one reason to change. That one reason to change facilitates loose coupling. And volatility-based decomposition achieves that all by itself. So what does that mean? Why do I care about loose coupling? A few years ago, I had an opportunity to work on a system like this. This is my textbook example of highly coupled software system. This system was in development for 7 years, never made it into production when I was there. 7 years in development, they couldn't even write off the cost. Everybody was a consultant on that. They had no internal software developers. They had a bunch of highly trained software engineers, but that lacked some architecture skills. Notice the data layer calling up into the code. This SQL Server can do this. This system did that. There's business logic repeated in the stored procedures, business logic repeated in obviously the business logic in the services, and in the JavaScript in the client. Every one of us on this project, every time we made a code change, we broke 5 things and we had to fix them. Right? I personally did that. I had 5 bugs show up despite my greatest efforts to figure out how to test this. That's the cost of a highly coupled software system. Okay, so this was dating back to like 2019 for me. This is a system I designed last year. This is an example of a loosely coupled system. So you don't know if this is good or bad. I understand that. All you can say really is that this is better than this one. Okay? But let me explain to you what this is doing. This is an analysis subsystem in this software system, and the way the data is coming into the system, the way the data is fed into the system from an external outside the company, is encapsulated somewhere else independent of what's happening inside this analysis subsystem. Now that data, there's many different clients providing data into this system, each one having their own file format that is coming in. And that normalization engine on the left encapsulates the rest of this call chain. And by the way, this is referred to as a call chain in the iDesign method for those that aren't familiar with it. That normalization engine encapsulates everything to do with the file format in one component. So if they ever introduce another client bringing in a different kind of data into this system, that is the only component that has to be made aware of it, the only place to make the change. The rest, the mapping engine and the validation engine are unaware because the mapping engine and the validation engine only see a normalized view of that data, a common internal structure that they represent it in. That's our logic layer representation of the data, the way we want to interpret that business logic. So even though the normalization engine deals with it, by the way, the normalization engine has a database behind it that's configurable. So they can set this up with rules that they don't actually have to have code changes. They just assign different rules to how they're parsing the different values in that database, or in that file that's coming in. So this is an example of loose coupling. The way the data comes into the system, the way the data is interpreted based on the various ways from different clients, and the way the rest of the system has to deal with it is all encapsulated. So that's system design. Let's look at detailed design. With detailed design, it's all about how we design the structure of the code within each of the components in our architecture. It defines how each service will interact with the data structures that we've passed between the components. So we first want to start with an interface-based programming model. Right away, one of the benefits we're going to get from an interface-based programming model is loose coupling. We're working with an abstraction over the implementation. The implementation should be able to change independent of the interface. Therefore, all the calling code on that interface can be unaware of the changes in the implementation. When we don't use it this way, then we force the clients to be changing with those components in our architecture. So interface-based programming model gives us that interface segregation principle from solid and the dependency inversion principle, right? We want to work with abstractions, not concretions. And then we also emit unique data contracts at each layer within our architecture, and as well as in between certain components. And so here's what this looks like. I'll show you, this is a sequence diagram, and sequence diagrams are often used to validate the detailed design work we do. And so each interaction is doing a conversion from a client layer representation to a logic layer, from a logic layer to a model, and back to a logic layer before it returns it back to a client representation. And what that does, it enhances our loose coupling with the client and the resources we're interacting with. So if we were to change the client or change the resources, the code in the middle can be insulated from that change, and therefore they don't have to change with it. They don't resonate. It doesn't ripple across our code base. I have done this wrong. I know what it's like when you don't do this. And it's painful. And of course, I volunteered to fix it myself because it was my mistake. I didn't properly encapsulate a resource access component talking to an external API. Okay? So I felt the pain, but I never made that mistake again. Once I realized the value this really has. Because you never know when it's going to change. So you can't assume you know, or you can't assume it will never change. This achieves that loose coupling from a detailed design level. Let's talk about highly cohesive. Forming united whole elements that belong together. So with system design, we have call chains. We have separation of concerns with those call chains, and the call chains are a composition, of use cases put together in a dynamic interaction of those components in a diagram, right? And so Yuval Lowy on page 70 says, a cohesive interaction between the manager, engine, resource access may constitute a single logical service to external consumers. And it looks like this. So if you're looking at what is a service to the outside world in the iDesign method, it's these vertical boxes here, these red rectangles. So I have a feed subsystem or service, I have an analysis subsystem or service, and I have administration subsystem service. This is also how we deploy things in the iDesign method, unless we're using a platform that allows every component in architecture to also be deployed independently. It all depends on your platform. But if you're just hosting things as a function app or an app service in Azure, then you would host it like this. If you're hosting each of these subsystems in, let's say, Service Fabric or within Dapper and Kubernetes, you might host each of these components in their own processes and have inter-process communication between them. It all depends on your platform. But regardless of that, each of these bounding rectangles represents a service to the outside world. Each one has a highly cohesive interaction that satisfies a set of related use cases. Let's talk about detailed design. Here we are again with an interface-based programming model. And now we're talking about service contracts. So with detailed design, the operations of each of our service contracts must belong together to form a united whole. That's the idea. So I'll give you an example of what maybe is not a highly cohesive service contract. Aside from the fact there's like 30 operations on this interface, this is a job info interface. And this job info interface has a few things that stand out. So I have get job by ID, I have get jobs by ID, I have get client job by ID, so on and so forth. But then I have this one here that says search metadata. That one seems a little different than the others. Now, it might be dealing with metadata pertaining to job information, so that's fair. But it stands out a little bit. So this might just be a smell. I don't know the use cases behind this interface. I didn't design it, I just found this. But ultimately, this smells as it may not have the cohesion we're after. Then let's look at this one here, get jobs for Vivian. Now, I didn't know if Vivian was an employee of the company, another software system, a developer's name, I don't know. But that one stood out to me as odd as well, that this didn't feel very cohesive. But not as bad as these down here. Get titles, get shifts, get shift lengths, get specialties. Now that one stood out as, that's far less cohesive. And as you can see, as I'm going down here, it's getting less and less cohesive. Down here we have ping, test error log, test log trace. Nothing to do with the job info interface anymore. Not by name anyway. Okay, so now just by looking at this, we can start to see by inspection, this lacks some cohesion. Things should belong together with the other operations in our interfaces. And I'll show you an example of a highly cohesive one later. Let's talk about logically consistent. Elements belong together and do not lead to logical contradictions. So let's look at our call chains again. These call chains are logically consistent throughout our entire architecture because we follow a set of rules and guidelines defined by Dvallo on pages 426 and 427 of writing software. And those interactions define that certain components can't publish events, certain components, or only certain components can subscribe to events. Certain components can't talk to each other. We don't have a resource access component talk to another resource access component, for example. Those interaction rules enable us to have a logical consistency. So here's a bunch of different call chains related to this system I mentioned earlier. It's bigger on your screen, you can see it. So on the far left here, we have a feed call chain. That feed call chain feeds into the analysis call chain. That analysis call chain both has a event-driven, system-driven workflow, as well as a user-driven workflow with a web client. And then at the bottom, we have these administration call chains. Now, each of these, collectively and individually, are logically consistent with the architecture and the interactions between them. All these pieces work together well. With detailed design, we have service contracts for all operations that belong together. Good contracts are always logically consistent, page 413 of writing software. So what we do to achieve highly cohesive, logically consistent interfaces or service contracts is apply the solid principles. We look for certain types of smells, those get bys and read bys in our naming convention hint to with a suffix of we are get by that, and all the bys by some different artifact within those data structures we're returning is a hint to we don't have a well-designed interface. So applying those solid principles can achieve that logical consistency. So we're back to the same interface again, and you can look at those same operations I highlighted before. These lack logical consistency with the rest of the operations. So let's look at extensibility, or extensible, the ability to extend a system for future growth. Now, extensibility is by far one of the most beneficial aspects of volatility-based decomposition. All right, so encapsulating potential areas of change into volatilities into components. New and changing requirements do not invalidate the architecture. So I went back to this same call chain I showed you earlier, this loosely coupled one. And I pointed out that the way the data is fed into the system is completely independent, encapsulated, separate from what this call chain is doing with analysis, analyzing that data and turning it into something that can be used downstream. This is actually a system that feeds another system. So this is highly extensible, and I'll show you here in a second what I mean by that. So let's say this is the data feed system, or data feed subsystem of this system. And I have SFTP clients and I have a web client. And you can see I have this event outside that feed manager that's just sending the file on a disconnected queued call down to the analysis system. Any changes happening to this feed system, the analysis system is unaware, right? That's that encapsulation of volatility we're after. So when I make changes to this feed system, I have the fewest number of places I have to make the change. What happens when I want to have an email client? What has to change in my system? Feed manager. Maybe I'll use another access component, but that's about it. The rest of the system is unaware of this change. Now I can add a mobile client. And literally nothing has to change when I add another client to the system. So here I am extending the capabilities of this system because of the way it was designed, not having a ripple effect anywhere else except for this one call chain. Has to make a change to accommodate the email client, the mobile client, and whatever other client you add. So now can you see how valuable this design can be in terms of supporting changes to the system? You have the fewest number of places to make the change, which is ideal, right? Let's talk about detailed design. We talked about extensibility. We talked about highly cohesive and logically consistent detailed design work. What we didn't talk about is some of those operations. When I mentioned solid principles, some of those operations can use a polymorphic DTO or data contract, leveraging Liskov's substitution principle, the L in solid, right? The L in solid represents polymorphism. So employed with a few design patterns, and looking at reusability across our use cases enables us to have a very extensible design. So here's a interface. This is an interface from my training program. It's an inventory management system. It has 3 different product types in it. It has commodities, it has salon products, and it has vehicles that are in inventory. And so we had, the original design was, well, we need CRUD operations for commodity. So I have 10 operations for CRUD for commodity. I have 10 operations for CRUD for salon product. And I have 10 operations for CRUD for vehicles. What happens if I want to add sporting goods to this inventory management system? I need 10 operations for CRUD for sporting goods. What if I add jewelry? I need to add 10 operations. That's the pattern we've established here with this particular design. So 30 interface operations right now with just those 3 components on the left are not easily extended. Now the interface on the right is one that employed the solid principles, looked for that reusability across use cases, used polymorphic DTOs. That's why you're seeing the find request base and the product base being returned. It's polymorphic. You pass in a request specific to a vehicle, I'll give you back vehicles. You give me a request that's specific to salon products, I'll give you back salon products. If you give me some attribute that's common across all products, I'll give you back a heterogeneous result set of a mix of commodities, salon products, and vehicles, right? Yeah, go ahead.
So your like find request base, that's kind of like that would basically cover a lot of these, individual query needs. Like it would have like a salon product name, blah blah blah, included in it.
Product name is what this one had, yeah.
Do you find that you need a polymorphic request base, that you actually have different implementations of a request base that might have different like criteria? Because typically I've had like a one object that had all my criteria to search for.
So great question. So do I really need to have a request base where I have to have another derived class that represents different request types, as opposed to having really one request object that has everything in it? And the goal here that we strive for is we do not pass anything to an interface that it isn't going to use. So everything in there needs to be used, because here's what happens if we don't. Some developer along after you is going to make use of it when they shouldn't. And so whenever I'm passing data between the components of my architecture, I create a new data contract with only what is necessary, because there will be this misunderstanding that they need to make use of something and it wasn't intended that way. And so that's the only reason why we want to avoid that.
Yeah, so every concrete implementation or derived class of the request base should be for one specific use case, and it's cohesive to regular use.
Maybe not one specific use case, but it is different than what the base class offers. The base class may have a set of common properties that's, in my case, in my inventory management system, that spans all of the different product types. But then I have a derived class that is giving me find request properties that are unique to a particular product type that doesn't apply to the others. So yeah, I could say I could do a request a base with VIN number, but that doesn't apply to salon product or commodities. So it doesn't fit. So it's not logically consistent or cohesive then. Even the data contracts need to apply the same principles. And so what we want, so there's really two things. Don't pass anything more than that receiving service should use in that use case is one guide. We also don't want to have what is referred to as God components or God contracts that has everything in it, because then it's confusing for the user to know what to set and what not to set. And what's required, what's not required, it gets to be kind of confusing.
Right. You don't want to just stuff all of that search criteria into one object that you pass through. It's almost
The other,
improved a little bit, but not a lot, probably.
The other benefit of having a derived class per find request is that derived type, the type of it, derives the behavior inside the component you're sending it to. In this case, I have a product accessor component that's using a strategy pattern based on the type of the request. And so I may have the common attributes that's shared code across all of them, but I have additional query parameters. I may add to my iQueryable, for example, because of the additional properties that's unique to a vehicle or salon product. Yeah, good question. Now, when you, oh, another question, yeah, go ahead.
It was different on this interface, so wondering why you're combining this is something that I was wondering, this kind of patching that I've seen, and I just started recently on that. Why we combine the create and update into the store? Because you have to jump through some hoops around with that store method, usually to try to detect if it's creation of a new object or actual update of
Yeah.
existing one.
Yeah, so why have the store basically encode, create, and update, right? It's like an upsert kind of concept in here.
Yeah, basically
Right.
why have store instead of create and update?
Okay, we want to use store because create and update work great for a database. Not necessarily a file system, not a cache. We want reusable service contracts, reusable interfaces across use cases. Nothing here tells you I was talking to a relational database system where create and update are distinguished. When I create a file, it doesn't matter. I'm going to overwrite the file. It's one call to save it. It doesn't matter whether it's create or update in that case. It doesn't have to. Or a cache. It's not a create or update situation. So we're using store as a very generic term, and we want to encapsulate the CRUD operations into the internals of our component and not expose them out through our interface. This enables us to have reusable contracts that can be reused beyond that specific type of interaction with a resource. It encapsulates the details of if we should to change how we create or update internally, we don't have to expose that information. So we're working with abstractions that as we enhance the system over time, the interfaces don't change, just the implementation does. And by doing so, we perpetuate that loose coupling and that high cohesion throughout the system. So you do need to distinguish between create and update internally of the component in the implementation details. Let's say if we're talking to a database especially, right, which this was for a database. But we intentionally want to hide the details about CRUD inside our implementation and take it out of our interfaces. We don't want to expose CRUD at the interface level.
Makes sense when you explain like that, because instead of now starting to work with this kind of one more class environments,
Yeah, this.
sometimes you have to jump through really strange hoops when you're dealing with the database specialists.
Right. But that should be encapsulated and hidden from the outside world. That's an internal detail. And again, if I was talking to a cache, I didn't tell you how I was storing this. Create and update wouldn't make as much sense, wouldn't be logically consistent. Store would. And so we started off with CRUD because that's generally speaking how we think about functionally what the system needs to do. But then we go to what is the proper interface factoring we want and have that same behavior but expose it in a way that as the system grows, emerges, and evolves, the interfaces don't change, and therefore the calling code doesn't have to resonate with the changes that do happen in the implementation. So on the left, we had 30 operations, and on the right, we end up with 3. The behavior that we have to implement is the same for both, but we have a much easier way of testing those 3 operations than we do the 30. We have to build the 30, we have to test the 30, we have to deploy the 30, and support the 30. We want the 3 because the 3 enables us to change our implementation independent of the interface, right? The dependency inversion principle from solid. All right, let's talk about testable. Testable is finding faults in the system by means of testing is easier. So with system design, one of the things we have is a single point of entry into the system. We will always go through a manager for any interaction with the back-end system. Each subsystem component is composed of individually testable components. With detailed design, using that interface-based programming model again, that interface segregation principle and dependency inversion principle from solid, and we have these service contracts and also known as interfaces for every component in our system design. Gives both of those together gives us what I'm going to show you, which is referred to as the spiral of tests. So each component can be individually unit tested. And then we can have components integration tests with a component and a live resource. And we're spiraling out from the internal unit testing of an individual component down out to a combination of a resource and a resource access and a resource, and then now multiple component interactions we're going to be able to integration test. Now I can integration test that engine working with that resource access component I already tested. And we continue to spiral out to we have a manager included. Now we have a use case level integration test. Because the bulk of the system is in the back end, we keep it out of the business logic, out of the clients. for good reason. The clients change the most. Now we're able to have use case level integration tests from the manager down. And then we can, of course, do system level end-to-end testing, commonly what QA does. Doesn't mean we can't write our own integration tests for this as well. And so our testability with this system design and detailed design approach automatically, by design, enables us to have a testable system. Maintainability. So maintainability is the ease of maintenance and coping with a changing environment, or coping with changes is easier. So let's talk about system design. With system design, we want to scaffold our solution so that we have a particular place for each of the components in our architecture, so that everyone always knows where to make a code change based on what is changing in that use case. So a highly organized code structure, aligning with the architecture. Solution scaffolding, promoting consistency and repeatability across the organization. Now, one of the great benefits of this solution scaffolding, if everyone is using them, is that we can facilitate an enormous amount of plumbing that we share with everybody through this mechanism. The plumbing is the piece the business is not asking you to do, but you have to do it anyway. You have to have plumbing to talk to a queue or a topic, to send messages, inter-process communication, call an API. Those are all plumbing. And configuration management, right? If I'm loading configuration, that's plumbing. We shouldn't build that. Every team shouldn't build their own plumbing. And so with this solution scaffolding, we gain that plumbing as part of this. Each service aligns with our architecture with a specific location in our code solution, so we always know where to make code changes. With detailed design, we're going to go back to this polymorphic DTOs and design patterns for enhancement enabling infrastructure, emitting unique data contracts at each layer. We started off again with this same interface, which is going to be easier to maintain as the system evolves. So I mentioned, if I was to add sporting goods and jewelry on the left, 20 new operations added to the 30 we already have. What happens when you add a fifth, sixth, seventh commodity, or product type? It just keeps going up, right? Your ownership overhead continues to grow. The interface on the right, does not change. Data contracts change. Implementation details can change. The interface doesn't change. This is how we design a maintainable interface and a maintainable structure for system design. So, as I mentioned, it is our job, whether we recognize it or accept it or believe it or not, our job as engineers to design and build loosely coupled, highly cohesive, logically consistent, service-oriented software systems that are extensible, testable, and maintainable. We showed you how system design and detailed design alone can enable that just by following the iDesign method. It comes out of the box with these capabilities just by following the information in that book, Writing Software. And all of this is part of a training program I have. I just thought I'd share this with you. If you want to learn more about it, reach out to me. We can talk more. Questions? Yeah.
Quick question about system design. A lot of that boils down to kind of, I would say we've seen similarities in best practices for like MVC, but I've seen like companies kind of say like MVC best practices don't work for us. Have you seen like if you put some more content behind it or like name it different that they're like it's acceptable? Like what's stopping them from going back down the, well we do iDesign, but iDesign doesn't work for us in these cases, and then you just kind of like end up with that spaghetti you showed at the beginning.
I'll tell you what Javal, so does iDesign fit all systems is kind of the question, right? Yeah. And do people accept that or say, well, it doesn't work for me?
Yeah, or it like decomposes to the point that you're back to where you're
So I'll tell you what Javal always said to that question in training. So I wouldn't design a device driver for my mouse this way. There are certain types of systems, certain control systems, this may be challenging for you. I know an architect in Switzerland that's struggling with that himself. And him and I've talked with him on many weekends. We're both part of the iDesign forum, and so we got together and talked about it. He's struggling because he's not working with the interface-based programming model. He doesn't get to choose the language. The vendors of the machines, the control machines he's working with they're the ones that control the languages. And he has Go and Python, all kinds of different things, C++. So not everything fits. I would say this, that what's unique about the iDesign method is that there are at least a dozen different architecture styles. Microservices architecture is one of them. Monolith is another one. Right? Monolith is an architecture style. Microservices, domain-driven design microservice is an architecture style. iDesign is none of those, and all of them at the same time, because it's use case-driven design. And based on your use case, it may look a lot more like microservices. I'll give you an example of a distributed payroll and billing system I designed once. Very much looks like microservices architecture. All right? But I have this other system I designed recently that just does printing for a major insurance organization, but it does printing. That's basically fulfillment. It's a fulfillment system. Looks a lot more like a monolith. But it's the term is modular. Everyone says, well, iDesign's a modular monolith. Well, you know what? It is still the right system for those use cases. And all we're trying to do is make sure that we're designing systems that when it changes, we have the fewest number of places to change it. It's easy to support, easy to test, doesn't take long to design or build, and we deploy the right things. So the common closure principle is something we all know about the solid principle from Robert C. Martin, but the common closure principle is things that change together to get deployed together. Well, I showed you those manager and accessor in that bounding rectangle earlier. Those get deployed together because they change together. Individually, that manager and that accessor by themselves are no use to the organization. It's only when you bring them together, because they were designed through a use case analysis. That's the reason they add value. They add value together. They don't add value. So it's the building blocks that you stitch together, right? They produce produce the use case or the feature, you might want to call it, the behavior you're after. Good question. Other questions? Yeah.
So at the beginning you showed that very scary picture.
Yes. And I meant it. It's a real system, so I had to live with it.
And I've seen similar systems throughout my career. My question is, I mean, is it possible to migrate it to iDesign principles?
Absolutely.
And what would be a strategy if you want to, if you have this in production running and you want actually to go from that to something that's,
And I've had that need in systems. It wasn't quite as bad as this, but it was bad, and it did have a lot of pain points, which is why we wanted a new architecture, because of the pain points that you're experiencing with that code base. First of all, this is the first resistance you're going to get. You have to design the system you want to move to first. You need to have the architecture, not of just a piece of it. The whole system, all of it. Because until you look at all of the use cases, you're not going to be able to analyze those use cases and come up with the proper decomposition unless you're looking at all the possible use cases you need to support. You don't necessarily have to build them all right away. You just have to design them, right? PowerPoint's cheap. I do all my designs in PowerPoint. The cost of a PowerPoint slide is just a few pennies, right? So design the whole system where you want to go. And then you have to pick what is either the most painful part of the system that you want to re-architect, or maybe the easiest to remove and lift over into a new architecture. Maybe the easiest thing to test is what you take first. But you want to use a strangler approach. Little by little, piece by piece, we're moving into the new architecture. Now here's what you have to be aware of, because I've done this. You have to support both the existing system and the new architecture simultaneously, get it into production, which means you're going to have data migration and you're going to have more work to do than if you were to just stop and rewrite it. So hands down, big bang is always going to be the fastest way to get there and the least costly. But that timetable is not acceptable to most businesses. So you're going to need to best thing to do is identify seams, some sort of partitioning, some subsystems in the current system. Even though it's spaghetti code, try to identify some seams that you can pull apart. Say, these things can be pulled apart with the least amount of resistance, and therefore we can re-architect just those pieces. Here's one thing I recommend, because I've had to do this. Write tests against the current system first to make sure the new architecture is performing the same behavior, because it's going to be very hard when you have a big system you're migrating to a new architecture to know you got it all right without doing that. So the first thing we did was we injected a bridged pattern in a way to produce data files within the system we had so that we can compare the results, the new architecture producing it and the old architecture producing it, and making sure we had an easy way for us to compare we got it right. Because if you have a lot of business logic, that's going to be the key thing you need to test. By the way, this is a very common need. It happens all the time, and it's very doable. Yes, sir. Question?
Alright, this is going to be probably a long question. But the analogy about building a house, like you wouldn't want to build
Just the
a
kitchen.
house. Yeah, like you wouldn't want to build a house before you plan it. You know, like you don't have a plan for your house and then build it. Usually, I buy a house by someone else that built it, and they might build it, I have no idea how, but we have laws and regulations that are very detailed that tell you and
Yeah.
force you
Code. Yep.
to have those designs and to submit them and document them and do all that stuff.
Yeah.
And that's why houses are built that way, because otherwise you could have a builder that says, I don't need that, and they can build you a horrible thing and sell it to you, and you might
Falls
think
apart.
it looks good, but it's totally worthless underneath.
Yep.
But I feel like that's how a lot of teams are right now, where they have builders who are not technologists or they're managers, and there's this huge Dunning-Kruger effect where they have like this tiny amount of knowledge, and then they decide like they know how to manage a software project or what have
Yeah.
you, and like, I mean, I'd love to do some of the detailed design, but it's really hard to sell to a business manager that where you don't have laws, and you don't have regulations, and you don't have any teeth that will force someone to pay the money to do that. So I'm kind of wondering like what your thoughts are there, and how you've managed to convince like managers or businesses that it's worth it to put in that work for like the upfront planning.
So system design has upfront planning, and so does project design. Detailed design, like you mentioned, is done during construction.
Okay.
I'll be honest, I'm very pushy, for one, but I don't give them the choice. In order for us to build this, we have to have this detailed design. Otherwise, we don't know what the structure of the code needs to be. And we could be coding it for weeks and weeks and weeks and not get anywhere. So we need some structure behind it. And so I'm often just trying to paint a picture as it, without this work being done, it's going to take us a lot longer, and we're not even sure we'll be able to test it. Like, paint the picture of the worst case scenario when you lack detailed design. Detailed design has by far been the thing that was most valuable in the architectures I've built recently, because it enabled us, like that interface I showed you, it enabled us to add things at the last minute before a deadline by 4 different developers simultaneously. We never could have done that without good detailed design. And so that's some of the power that that manager needs to be aware of. Like say, well, you know what, if we ever needed to hurry up and get something done, that detailed design is going to be able to get us there. Otherwise, it's going to be months added to this. So I had one, I know I've told you this before because you were in my training before. Well, I had this one, we had 4 reports that this team, the business told us we needed, and we had 2 sprints left before the hard deadline. It was a year and a half in the making. 2 sprints, 4 weeks before a deadline. And they said we can't go live without these 4 reports. And we just happened to have done good detailed design, like we did everything in that system all the way through. It did nothing different, but those 4 reports got added by 4 different people in the same sprint, without any bugs and side effects anywhere else in the system. And the only reason we were able to do that, purely because of detailed design. So detailed design does have a lot of value, but you're right. It's just going to fall on deaf ears for people that don't quite understand the complexity of what code gets to when we don't do the work. So I generally, like I said, I don't usually give that choice. I don't say we're going to skip detailed design.
The time isn't that much more. I mean,
I would say, yeah, the time to do detailed design is more than system design, to be fair. It does take longer, but so does writing code. And think about it this way: if you were to write the code without a design, without any structure, no design patterns, no interface factoring, just start writing the code. They might iterate on that code for weeks before they get it right. But so just a little forethought by somebody who's experienced at thinking this way goes a long way to giving that guidance. And by the way, the sequence diagrams I showed here, those are the guides to implementation for the developers. And then you do a handoff meeting with that developer and say, well, here's what this operation needs to do, and you may even put comments in your code when you check it in. And by the way, detailed design is a code-committed completion work, right? You code review it, you review it with the developer if you can. It often saves you more time than it takes you. But if you were to do detailed, and Javal's got videos on this, if you do detailed design all up front, like he did on one project, it took him, and it was him and several other architects, 4 months, full time on detailed design of a system. And he talks about all the metrics and how perfect it was. He's very detailed, right? But I don't think anyone would tolerate that. That's why we do it with the sprints, with the code. I might do detailed design this sprint, implement it the following sprint. That's generally how I like to structure it. Not everything needs detailed design. If you're not changing interfaces and data contracts, it's just implementation, just implement it. You might not need it. You might give some guidance to the developer, but not every, and I've seen that now. One of the teams I worked with, that same system, I was on another system outside in the same company, but on a different system for a year, and then I came back and I realized, well, now he's doing detailed design on everything. Like, well, we don't need to do detailed design if we're not changing interfaces, and if there's not new interactions between the components in our architecture, it might not justify the detailed design effort, because you're doing 90% of the work during detailed design, just commenting out the code, and the developer just uncomments it and write tests. That's what was happening. So that's probably going too far. That's not design work anymore. It's implementation work. This is pre-implemented. Go ahead. Question? Sure.
Not necessarily the best manager is going to be doing that, but most managers are out there, they're going to do that. They're trying to impress their management by getting the system done as fast as they can. And I think it's our job to push back on that, provide that balance against that pressure to tell them, like, if we build it this way, you're going to look bad in the long run. It's going to be not good for you, it's not good for me. Let's think about it. So obviously, like, Jim has spent a lot of time thinking about this and has prepared answers for all of these scenarios, right? I think it's important that we all think that way and think, like, not when we're right in the moment in front of the manager and he's telling us, we got to get it done. We have to have reasons for why that's not the right thing to do. And so, I would just encourage you with those comments. It's probably just like an education mindset shift sort of thing.
Yeah. There's a cost, right? You pay now or you pay later. When you pay later, you pay much more than if you were to pay. So if you want to be proactive, you do design. If you want to be reactive, fixing bugs in production, refactoring, that's the cost, right? But you're going to pay. So I would rather be proactive, pay up front with a little structure, discipline, and with proper design techniques that are going to enable me to add features in perpetuity and not increase the time it takes to add every feature. So software should not get harder to enhance over time. It should stay the same. All other engineering disciplines work that way. Software doesn't, simply because we don't do design. All other engineering disciplines also do design first. But I am on a project right now, just met with the team this morning, and they want to start writing code. I said, well, show me your design. Well, it's simple. We don't need one. They're building the future of the systems platform, okay? I know this. I talked to the manager last Friday about this system. And I insisted. I said, no, we have to understand. I was talking to some people before this presentation about the same thing. It's like, we have to understand what are the use cases before we can do they didn't even bother. They said, no, we just have this one. I said, you don't have one. I know you don't have one. You're developing a platform that has hundreds of use cases, but they just want to build the one. Well, you can build just the one feature, okay, the one service to the outside world, right, external service. But before you do that, you have to design for all of the capabilities you need to have, because you don't know what the components are without doing that. So that's a learning curve. They're not used to it. They're not used to anybody pushing back saying, we can't do that. We can't just write code. Oh, it's easy. I mean, yeah, I know it is, but you're going to rewrite it over and over and over again. And I was hesitant to ask this question. How many times is your employer willing to pay you to write the same code? 15, 20, 30? Is that okay? Are you okay with that? Writing the same code over and over and over again? That's what happens when we don't have a design. And that is the cost of software. And it's hidden. The problem is with management, it's hidden. They don't see that you're rewriting that code over and over again. They just know it's taking a long time. They don't also know, they may not see, I know this because one company I work with, we measured rework. It was 80% of the work we did was rework, touching the same lines of code over and over and over again. An example of a bad design. That's why we were measuring. We were trying to figure out why is it taking so long? Why is it so hard to support this software system? And this is right before we employed the iDesign method at that company. And we took a subsystem and re-architected it. And before we re-architected it, we had tests to make sure we knew the outcome. Right? So that's exactly where that's coming from. That was back in 2015 that we did that. Great questions. Yeah.
Probably find it my own views, but let's say you have, there is architecture, let's say in the world of domain-specific microservices, how would you apply iDesign? Would it be like you still, for each service, you would have this breakdown, or maybe every service is going to represent one of the pieces of iDesign architecture?
So the domain-driven design is designed by domain entities, right? So centered around that, the entity is in its world of its own. Let's say, for like say an insurance example, it's a policy. Insurance policy might be my domain, so I'm going to design a policy service. And it's going to have its own database, right? It's going to have its own context of execution. Okay. What is the business use case of policy by itself? How does the business shareholders earn more value because you produced a policy service? It stands out in the middle of nowhere doing nothing by itself. It's not until you interact with some other services, right? Okay, but those other services somewhere, somehow, have to turn into the execution of a use case that adds value to the business so they can sell more, so they can earn more value, right? Everything we're doing is to earn shareholders more value for the companies we work for. So, when you take a use case-driven approach, then you're going to have the components of your architecture that make it easier for you to support changes to the software system with volatility-based decomposition. With domain-driven design, it is a technical-oriented design. And it by itself doesn't serve the business community until you add something on top of it. Expression APIs, I think they call it. There's a term for it, right? Anybody know? Expression APIs? Is where the business logic is that stitches together all those different services. But then you end up with that spaghetti of services I showed you earlier, that highly coupled system. You have high degree of coupling. And so now when you need to deploy something, you can't just deploy one, or you have to test everything together. You have to do a complete regression test every single deploy a single component. Uber went through this in the early 2000s. They had 22 mission-critical microservices, 2,200 mission-critical microservices. They had 2,000 developers supporting it. They got to a point where they couldn't deploy anymore. The integration testing was eating them alive. Months would go by, they couldn't deploy. Because they had this. They had domain-driven design microservice architecture. And the whole point is that we shouldn't have thousands of services. We should have tens of services in our systems. Now, you can have different systems, each one having tens, that interact with each other externally. But when you have one giant system all talking to each other with inter-process communication, then you just have a mess on your hands. Hard as heck to test and validate, as well as build. Because all those integration costs. That service could be called by 50 other services when you have 2,200 mission-critical microservices. 50 other services need to integrate with your change. When you change it tomorrow, 50 other services have to be retested. And you hope you find all 50, right? Maybe there's 51. Did you miss one? That's the risk. So it's a very different approach, right? Domain-driven design is based on the domain, and volatility-based design is based on the use cases, right? It's use case-driven, domain-informed, context-relative, is how Monty Montgomery would say it. It's use case-driven, domain-informed, and context-relative. The context is relative to the caller. If I have an internal application, I may expose a lot of capabilities to that internal caller. But if I have a public-facing client, I may limit what they're able to do. Good example that that Monty Montgomery gave in training was, I may have a restaurant website. The restaurant website is going to have a manager in the back end. I may expose one interface facet internally so they can change the menu, change the hours of operation, change the pricing on their menu. My external facing interface of that manager is going to have, I can view the menu. Doesn't have any other stuff, right? That's the context. Based on context, I can instantiate a different implementation of my service. That's that context relative piece.
So basically, I'm just trying to summarize. And again, this is something from my previous experience. You're describing when you're saying that everything talks to each other. This is exactly what I've seen and it was really messy. So basically, step out of this approach and step out of the domain-driven approach and just design and use cases.
The use cases own the data too. Keep that in mind. We design our data based on the use cases, not on the entities. And so everything is use case driven. So once you've experienced that, it gets easy. But it takes a bit of work to untrain your mind from the way you've been doing it. And that's what this team was experiencing. I want to build the feature, and we can't build the feature. We don't have a design to build that feature. Now, this organization is going 100% in the direction of iDesign, the iDesign method, okay? So that's already a foregone conclusion, which is why I'm in the conversation with them. But the point is that they're not used to thinking that way. And so it takes a bit of a mindset shift. It does. And I'll be honest, I had to go through it myself at one point. After 20 years building it like everyone else, I had to learn this. And my first system wasn't great. But I was constantly trying to learn, and I get lots of feedback on that system. And we improved it right away. But I had to get that feedback. And so that's what you need, is you need somebody else who's done this before to give you that feedback. And you can course correct very quickly, very rapidly. System design is very fast. I did a system yesterday, and maybe I had some rough draft call chains, but it probably took me 3 hours. And I'm ready for the team to review it with me on Monday. Only because we spent weeks gathering requirements. Okay, so I didn't tell you that. Weeks for gathering requirements, but hours to design the system, simply because we focused on the use cases the whole time. What are the system-driven workflows? What are the user-driven workflows? I have pictures of all the screenshots of all the UI, so I can make sure that my design, my call chains satisfy every single interaction, every button on that UI, because it has to, right? I may not even build all those screens, but I want to make sure I know how the design of the system can support it in the future. So the idea is design big and build small goes a long ways. You don't have to build the whole system, but you do have to design it.
I'm just going through this mindset change where I'm just working at design, so this one.
One of the things that that's great about decomposition is that you can focus on what is the component necessary to achieve this one specific thing I need to do. Like that normalization engine I showed you. I didn't call it normalization at first, but I think I call it transformation or something else. But it was creating a normalized view for the rest of the whole ecosystem, and that system would understand the data, but what's coming in is completely different, right? And that was the idea, is like, hey, just when we build just normalization, it was a beautiful thing, because you don't have to worry about what anything else is going to do in the system. I just had to normalize. I needed to come a common internal structure of any file format that comes in the door. And so now we've encapsulated. And then we've defined a few database-driven rules that you could easily stitch together for some other, like a CSV file, right, or an Excel spreadsheet, whatever it's coming in as, we had good ways of interpreting that data. And all of this was flat files that we were dealing with, so it was relatively easy. There's different columns with different names, but they had different mappings to them. That could be done by a tool, an administration website, so that a non-developer can arrange a new file format and consume it. And the rest of the system didn't have to change for any reason. But if we did have to make a code change, it was still in that one component. So that's one of the things with decomposition is it takes a big problem, all these use cases, and it breaks it down into something very compartmentalized that's easy to reason about, build, test, and maintain. And just keep doing that on every single one of them, right? But first you have to come up with that volatility-based decomposition, which is driven by the use cases, which produces the core use cases and potential areas of change, which produces the decomposition into the components in the architecture. So it is a step-by-step process. Other questions? Yeah.
Have you run into situations where use cases change after a couple of years?
Use cases are always changing. That's the reason we use volatility-based decomposition. That's exactly what we're insulating ourselves from. So the use cases are always going to change, right? That's to the business, it's the requirements are changing. To us, they're just use cases, right? The use cases represent the required behavior of the system. So use cases are always going to be changing, and the reason why we want to use that the approach to volatility-based decomposition is we don't want to couple our design to the requirements. We couple it to an abstraction over those requirements by looking at all the use cases and abstracting out from that something higher level, more generic, that will satisfy any change to that. So data feeds are a really good example. I could email you a file. Tomorrow I can have a mobile app send in a file. You can have a website send in a file, right? I can SFTP that file. All of it is encapsulated behind the data feed. Now the rest of the system has to process the file, but is unaware of the different ways it came in. And I will even go so far as to say, well, everything's going to queue a message to the analysis system. I don't care how it came in, you're going to queue a message over there. You're going to put it, whatever. If that file's too big to be able to pass on the message, put it into storage, and then queue a message telling it where to get the file, which is exactly what that system I showed. But the requirements are always going to change. And the key is to make sure that we have the right decomposition that makes it so it's easy to handle change. Change it all day long, you know. We're gainfully employed for years to come because the requirements are always changing, right? We'd all be out of jobs if requirements stopped changing. By now, someone would have built every system we ever needed. So it's a good thing they continue to change, right? Software's almost never done. Have you ever noticed that? It's not like, okay, we're done. We're never going to change it again. I've owned no system that did that. They are always changing it. And because of that, that's why we need to employ these design techniques, is because they're always changing. Because it's changing, right. And there's new needs all the time. Because the business needs to grow, and they're using software to accelerate their revenue, right? It's not necessarily, most of the companies I work for are not software companies, right? They have other products they're using software to help them get out to the world, to the users, right? And it helps facilitate and accelerate their business. So it's wonderful. But, I mean, we have more software in our future than we have in our past. We've been building software since 1970s. I mean, and even then it was mainly universities and the government back in the 1970s. It wasn't even mainstream, right, until the 80s. I wrote my first software in 1984 on an Apple II Plus.
The reason I asked that is that abstraction, I wasn't sure it was overly clear that it said why you design on use case.
Yes. We don't design directly against the use cases. That's a fair, I did not get into those details, but yes, we design against an abstraction of those use cases, but in order for us to know what that abstraction should look like, we need to understand comprehensively all present and future use cases. That team I was working with today was just, this is the one we need to build. I said, I know that. That's all you're going to need to build probably in even next year maybe, but you know what? if you have that, if the need shows up next year or 9 months from now to one of the other use cases, we need to have a system that supports that too. We have to, and in order for us to get to the abstraction of the use cases, we have to know what they are. So, and it can take a while depending on the company. I've seen, I worked at Kiwa Corporation once, and I still, to this day, the best experience I've ever had of interviewing business owners was at Kiwa Corporation. These two, you were in the room, I think. You may not remember this, but these two business owners knew the systems and the pain points so well, they couldn't wait to tell us. I mean, they were just excited to be in the room, right? And I was just doing my job. Okay, I'm here to gather, we call it interviewing. We're interviewing the business about the use cases. I was up at the whiteboard, and I was writing all this stuff down. I had one follow-up meeting that surfaced up a new component architecture. One, I don't know how long it was. It might have been 4, it felt like 4 hours of writing on a whiteboard. But we had all the use cases written out well enough for me to extrapolate a design based on volatility because of the way they were so clear about what they wanted. And I have yet to find any other organization that's that clear about what they want. That's the hard part for a lot of companies. I don't know what I want. A lot of them want to follow Agile. Agile should be for business agility, not for iterating on what you want. That's proof of concept. Maybe you do some wireframing. Don't build the system. Do you remember what that system was? I don't even remember. Yeah, I don't remember what the system was. It was, well, that was my last system at Kiwa. But no, Geotab was a completely different one, and there were, that was a multi-team effort. That was very different. That was one where I really shined doing project design on that one. But now it was before that, but it was the same month. It was in January, and I think that was late January. I started January 2019, but earlier in January, maybe December. But it was there were two women in the room that were either product owners or business analysts. I can't remember now, but they just very clear about what they want. But it was so easy. I was done hours later with the design. It was that easy because they knew what they wanted. But I've never experienced that a second time. That was the only time that somebody knew exactly what they wanted their system to do. They've been thinking about it, I think, for maybe months or years. You were in the room, and I want to say Brian Olson was in the room. I don't even remember for sure, but it was one of the first. And we were all there, kind of learning the iDesign method at Kiwa at the time. And I had come back from Architecture Clinic in November of 2018, and so I was ready to go. Like I was eating this up, this opportunity, and I had 4 designs at Kiwit after I came back from the architecture clinic immediately. Like I said, I've always been in a position to put into practice what I learned from training. And right away I had 4 different systems designed. One of them wasn't mine, I was helping somebody else, but to be fair, I was participating in that. And that was very valuable to like immediately not forget anything, just hit the ground running with what I'd learned. And I think I told Matt, I says, I was overcomplicating this, overanalyzing it. Analysis paralysis. Once I learned the techniques that you identify all the use cases, identify the core use cases based on those use cases, an abstraction of them, and the volatilities and your non-functional requirements as your interview notes that drives the scalability, performance, and those kinds of things that are non-functional, all those things really quickly can help you with that design effort. And I do show this in a very simple system, but I do show this in my training to really make it clear that it can go fast. It is fairly simple, but it does require a different thought process. I thought I was going to be done in 30 minutes. Good. All right. Well, thanks everyone. Good questions.